Day 586 of doing a LeetCode problem every day until I get a job. All right, y'all, we're back again another day, another LeetCode problem where we're doing daily LeetCode problems. And today we have question number 3577. Count the number of computer unlocking permutations. The difficulty level is medium, but don't worry because you already know we're going to keep the solution as simple and easy to understand as possible. But before we get started, y'all, don't forget to like, hype, subscribe, comment, and share. And if you need any new Apple AirPods, go ahead and check out that link in the description so you can get you some. Now let's see what the question says. You are given an array complexity of length n. There are n locked computers in a room with labels from 0 to n-1, each with its own unique password. The password of computer I has a complexity of I. The password for the computer label 0 is already decrypted and serves as the root. All other computers must be unlocked using it or another previously unlocked computer following this information. You can decrypt the password for the computer I using the password of J, where J is any integer less than I with a lower complexity, i.e. J is less than an I and complexity of J is less than complexity of I. To decrypt the password for computer I, you must have already unlocked the computer J such that J is less than I and the complexity of J is less than complexity of I. Find the number of permutations of 0, 1, 2, all the way up to n-1 that represent a valid order in which the computers can be unlocked, starting from computer 0 as the only initially unlocked one. Since the answer may be very large, return it in modulo 10 to the 9th power plus 7. Note that the password for the computer with label 0 is decrypted and not the computer with the first position in the permutation. All right, y'all, so that seems like a lot to take in. So let's go ahead and take a look at these examples just to make sure that we are doing this problem correctly. Now, before we get into example 1, the first thing we want to understand is what is a permutation. It says a permutation is a rearrangement of all the elements of the array. Okay, so now that we know what a permutation is, let's take a look at example 1. In example 1, we have complexity equals 1, 2, an array of integers 1, 2, 3. The output is 2. The explanation says the two valid permutations are 0, 1, and 2. 0, 1, and 2, meaning this is just index 0, 1, and 2, right? So it says unlock computer 0 with the root unlock computer 0 first with the root password. Boom. So we can unlock this computer right here with the root password. Then we're going to unlock computer 1 with the password of computer 0 since complexity of 0 is less than complexity of 1. So since complexity of 0 is less than complexity of 1, that means we can unlock computer 1 with the password from computer 0. Boom. Then we're going to also unlock computer 2 with the password of computer 1 since complexity of 1 is less than complexity of 2. So also since complexity of 1 is less than complexity of 2, that means we can unlock computer 2 with computer 1. Boom. But that's only one permutation, so we can add this permutation to our count. Now we have one permutation. This right here is the second permutation, and we do this one a little different than we did the first one, and I'll show you how. So for this permutation, we're going to unlock computer 0 with the root password. Boom. So we unlock computer 0 with the root password. This computer 0 is unlocked. Then we're going to unlock computer 2 with the password of computer 0 since complexity of 0 is less than complexity of 2. So since this is 1 is less than 3, that's going to allow us to unlock computer 2, which is this computer right here, with the password of computer 0. Boom. Similarly, we can unlock computer 1 with the password of computer 0 as well, since complexity of 0 is less than complexity of 1. So since 1 is less than 2 and 0 is less than 1, that means we can also unlock computer 1 with the password from computer 0. Unlike up here, you can see we did it in order. So first we unlock 0, then we unlock 1 with 0, and then we unlock 2 with 1. But in this case, we're unlocking both 2 and 1 with 0, right? We're unlocking computer 2 with 0, and we're unlocking computer 1 with 0. But we're allowed to do that because they fit the requirements, right? Because in both cases, j is less than I, and complexity of j is less than complexity of I, right? So in this case, 0 is less than 2 and 1, boom, and 1 is also less than 2 and 3 up here. So that's why we're able to do it like this. Now, just in case that didn't make sense, let's take a look at example 2. Example 2 is an example where there are 0 permutations that can unlock all computers. So in example 2, we have complexity equals an array of integers 3, 3, 3, 4, 4, 4. The output is 0. It says there are no possible permutations which can unlock all computers. So, all right, y'all. Now that we understand the question, let's get into the fun part, the actual solution, y'all. Solution is not that difficult at all. So let's get into it. Now, the first thing we want to do is we want to handle this modulo 10th to the 9th power plus 7. So for that, we're just going to say, we can come right here, we can say let modulo equal 1 underscore 000 underscore 000 underscore 007. Boom. So when I do this, I see this 9, so I just know that should be 9 zeros. But then this plus 7 lets me know we're just going to put a 7 where that 9th zero would be. Boom. Then we need a final answer to store our result, right? Or we need a place to store our final result. So we're going to declare a variable called result. We'll cast that as an integer, and we'll set that equal to 1 as a default value just to start. Then we need the number of elements in the input array. So we're going to say var n colon, and so we're going to cast that as an integer as well, and we're going to initialize it with complexity.count to start. Boom. Now we need to iterate through indices from 1 to n minus 1. So we're going to say for I in 1 less than n, we're going to open up the brackets. And if any complexity value from index 1 onward is less than or equal to the first element, then the permutation condition is invalid, so we're going to return 0. So we're going to say if complexity square bracket I is less than or equal to complexity square bracket of 0, then we're going to come out here, we're going to open up the bracket, and we can just return 0. Boom. Then we'll come underneath this if, and we're going to multiply the result by I, which is the number of valid positional choices so far, and apply the modulo to prevent overflow and maintain a modulo constraints. So we're going to say result equals, open up the parentheses, result times I, come outside of that, and we're just going to say modulo. Boom. Now, if all complexity values were greater than the first, then the number of valid permutations is n minus 1 modulo the prime. So we could just come right here and we could say return results, y'all. Boom. That's all she wrote. Let's give it a run. Make sure it runs properly before we submit it. Let's see, it's accepted. So let's go ahead and submit it. Make sure it's still accepted after we submit it. Let's see, and look at that, y'all. 0 milliseconds beats 100% of users. That's what I'm talking about. That's what I like to see, y'all. So with that being said, I hope y'all learned something today, and I hope to see y'all here tomorrow for another day, another LeetCode problem. See y'all then.